some of you. Okay, we are shifting into evolution. Okay, you've heard about us evolutionary biologists before. We are very crafty. You'll notice I didn't say evolution in the abstract, but here you are. You're going to learn a little bit, which reminds me of the famous bumper sticker, which says something to the effect: "If evolution is outlawed, then only outlaws will evolve." Okay. So let's not be outlaws. Let's evolve together. Number one, was there a unique Middle Eastern genetic markers in the source population? Okay, what do we mean by genetic markers? Well, I tell my students all complicated issues in evolution can be explained with candy. Okay? My undergraduates are very good at understanding things based on candy. So let's talk about some candy. What I've got here are these gumball machines. I've got 4 gumball machines filled with different colored gumballs. The gumball machine represents a population. The gumball is a single genetic marker, and the color is a variant of the genetic marker. Now, when we look at these sorts of data, we're looking at more than one marker, but this is to illustrate the point. Okay. Now, if you have a collection of gumballs which look like this, we refer to this as discrete data. And that's because gumball machine number 1 has only one kind of gumball, number 2 has only one kind of gumball, and so forth. Okay, straightforward, you got it, right? So it's easy with candy. If we were talking genes, you'd be lost, but it's candy, right? Okay. Well, that's not the way the majority of the data are that we use to infer these historical events within populations. The majority of the data are based on frequency data. And what frequency data means is that you could have 4 different gumball machines, 4 different populations, A, B, C, and D, and they are defined by the frequency of the different genetic markers which are present. So for instance, you might take a look at gumball A and see there's a lot of red gumballs. Machine B's got a lot of yellow gumballs, I think. D's got different colored gumballs. Boy, can you actually see those colors? Okay, beautiful. You're following along, wonderful. Okay, this is called frequency data. Now, the implications of using discrete data and frequency data are very different. And both kinds of data are used in these sorts of analyses, but the preponderance of evidence thus far has been based on frequency data. Okay, so the first point you'd have to satisfy me with is that you had a source population which had distinctive genetic markers. You were able to determine what these are before you go in with your study. Did founder effect skew the frequency distributions of genetic markers? Okay. Sounds fancy, sounds difficult. It's really not so hard. Imagine you were the proprietor of these gumball machines, and you had one gumball machine with a faulty mechanism. So you walked in the morning, and you saw gumballs on the floor. Okay, these are the colonizers. Okay, these are the ones seeking out, trying to find a better life, right? Okay, they're leaving the gumball machine. What is your inference? Where did this come from? It came from B. Well, you're like my undergraduates. You don't want to yell out and stuff, okay? B. It came from B. And this is fairly obvious, and this is fairly straightforward, right? Well, let's talk about frequency data. We've got our 4 populations, A, B, C, and D. And I've gone through and I've carefully counted the gumballs in each, and we have 4 different colors with different frequencies. Now, can we define these gumballs based on these frequencies? Can we define these gumball machines? Well, certainly you can. You can say that A has got half of them yellow, 25% red, 15% green, 10% blue, and so forth. Okay? So these are the things which are defining our actual populations. Well, let's presume that we have an infinite-sized gumball machine, which is something I dreamed about as a kid. And let's presume that the mechanism is really faulty, so that when you wake up in the morning, there's 1,000 gumballs on the floor. And when you count up the 1,000 gumballs, this is what you get. Okay, doesn't it sound like fun research? Yeah, this would be like an ORCA-funded project right here. Okay, so we've got 1,000 gumballs. You count them up. What gumball machine did they come from? Why did they come from, C? They closely match that frequency. Why is the frequency not the same? Ask my brother. David. Random sampling. Okay? I love having a statistician in the family, by the way. It's kind of like having a doctor. I don't have to worry about learning statistics because I bring all my problems to him. Yeah, random sampling. Okay, so it's not the same as C. It's pretty close to C. We will infer it came from C. Okay, 100 on the floor. Where did they come from? Okay, they came from A, but the distribution is more skewed. Frequencies are more skewed. Why are they more skewed? Smaller sample. Marvelous. See, you guys can pass evolutionary biology. This is great stuff. Okay, C, 10 of them. There's only 10 on the ground. Where did they come from? Is it starting to blur a little bit? Well, you could say C, maybe. Or maybe you could say they came from something else. Okay, I'm going to give you a hard one right now. 3 gumballs. Where did they come from? You have no clue, do you? Okay, and why do you have no clue? Because you have sub-sampled this population and you have sampling error. And your sampling has been very small. Therefore, the point I'm trying to make here is that undersampling of genes skews frequency distributions, hence obscuring history. That is what founder effect is. Okay? If you have only 2 or 3 people loading up in the station wagon, going to the new world, and they have subsampled this population, how good are you going to be at accurately representing these frequencies? You're going to have a hard time. Okay, let's keep going. Genetic drift. Genetic drift is a similar idea which further obscures frequency distributions. And genetic drift works kind of like this. Assume 1,000 gumballs. Okay, doesn't that sound like a good statistics problem? Assume 1,000 gumballs. Okay, they're here at this frequency. Go in and select 100 gumballs, and you get a different frequency. Fill up a gumball machine using that same frequency. Okay, so you picked 13 yellow ones. Now you're going to fill that new gumball machine with 130 of them. And repeat. What's going to happen to you? What's going to happen to the frequency, guys? It is going to change. You're going to start like this and go to something like that and go to something like that and go to something like that. And in fact, some of these gumballs will disappear altogether because you did not happen to sample them. This is what the original looked like. This is what it looks like after genetic drift. What happened? Frequency distribution was skewed because it further skews the distribution of these genetic markers. Now, you've got to realize that this is a notion which is well entrenched within evolutionary biology. This is how we think new species are made, because we recognize that this has such a devastating effect on the underlying genetic signature of colonizers that they can change sufficiently over a long period of time to make new species. Okay, this is really an important concept. So you got to satisfy me on this. Let me give you the classic example. Do you have any freshmen here today? Oh yeah, we got one in the back, 1 or 2. Right. Let me give you an example, see if you can catch on to this. What I want you to do is sit right back and you will hear a tale of a fateful trip that started on this tropic port aboard a tiny ship. Now the mate was a mighty sailing man and the skipper brave and true. 5 passengers set sail that day for, how long was it? A 3-hour cruise. Oh, you guys are so educated. Okay, if this were my evolution class, I'd have you sing the rest of it and then we get up and hug each other and stuff. We won't do that. Gilligan's Island. Okay. Gilligan's Island. Gilligan's Island. My father used to make fun of me for sitting and watching this hour after hour. He didn't realize that this would be the foundation of my science. Okay, Gilligan's Island. Do we have anybody here from Hawaii? Anybody who grew up here in Hawaii? Wonderful. Is that you, Keone? Okay, marvelous. Stand up, Keone. Keone is one of the graduate students who works in our program here. Well, have you watched Gilligan's Island? No, you haven't? Oh, and you think you're educated. Okay, we won't ask you this question. Let me ask you a question. How many people were on the boat? 7. Okay, can you name them all? Well, of course you can. I'll give you some help. Okay, 7 people on the island. Keone, you grew up on Molokai, right? When you went to high school, did you have a name for individuals who looked like this? They're called